Okay, so before we start example 12, this kind of is in line with what we just did in the warm-up. Kind of the same thing that we did for sine and cosine. Whenever you're composing a tangent and its inverse, inverse or arctangent, in either way, under some circumstances, it may just undo itself. So, on the top one, tangent of arctangent of x. That x represents a what? Angle or a ratio or something else? It's a ratio. Good. What are the legal ratios for arctangent? All real numbers. Tangent could be any ratio. So the domain of arctangent is all real numbers. So this should equal x when? Always. Good. Always. This one is the only time it's always just going to undo itself. Tangent of arctangent of anything will always be that something. Okay? Because the domain of arctangent is all real numbers. But as we just saw in the warm-up, it's not necessarily true the other way around. Arctangent of tangent of x, this x represents an angle. Okay, and the PVR for arctangent, because it's the last thing we're doing, is between negative pi halves and pi halves. And notice there are no equal signs here, right? So we cannot actually get to pi halves or negative pi halves. So as long as we start with an angle that is strictly between negative pi halves and pi halves, it will undo itself. But if it's outside this interval, or as we saw in the warm-up, if it equals pi halves, then it's D and E. Okay? I'm sorry. There are two cases. If it equals pi halves or 3 pi halves or 4 pi halves, then it's D and E. If it's something where tangent actually exists, then we have to figure out what the angle is in the PVR. Okay? So let's throw a separate example up here real quickly. Let's call this 0, example 0, so we can get it on the recording. What if I have arctangent of tangent of negative pi halves? What's that? D and E. Very good. Because negative pi halves is down there with 3 pi halves coterminal with, and that's where tangent is undefined. And so because my input is a vertical asymptote, there's no way to take the arctangent of something that doesn't exist. Okay, so if you were to work it out from the inside out, it would look like this. It would look like arctangent of D and E, which of course then is D and E. One D and E kind of ruins the whole party. But what about this one up here, part A now? Inverse tangent of 7 pi fourths. Is 7 pi fourths in the PVR for arctangent? Is it between negative pi halves and pi halves? No. Is this one going to be D and E though? No, this one's not D and E because 7 pi fourths is a defined tangent angle, unlike pi halves. So in this case, we have to do what we've been doing. We have to figure out where 7 pi fourths lives, which of course is where? Quadrant 4. And we need to get to quadrant 4, but like arc sine, we need to get there by going not all the way around, but rather what? Straight down to it. So I know it's going to be what? Negative pi fourths. The reference angle for 7 pi fourths is pi fourths. So I need to get to quadrant 4, but I need to get there by going clockwise by the acute amount, negative pi fourths. Okay? Arctangent and arcsine have the same PVR for the most part, except up at pi halves and negative pi halves. Okay, letter B. Tangent of arctangent of negative 1000.22. What a cute number. I'm starting with what, an angle or a ratio? A ratio. Is it a legal ratio? What are the legal ratios for tangent? All real numbers. Is that a real number? Yes. Okay. So that would be just the number. This is the one we saw up above where it always undoes itself. As long as it's a real number. What if it was tangent of arctangent of 11? Is 11 a real number? No. I wouldn't ask you that either because that's a silly question. That's called a bad math joke. All right, letter C. Arctangent of negative 4 pi thirds. We're starting with a what? Starting with an angle. Tangent of that angle is going to give us a ratio, and then the arctangent of that ratio is going to give us an angle in the PVR. Is tangent, first of all, defined at negative 4 pi thirds? Or is that a vertical asymptote? It is defined, but it's not in the PVR. So let's figure out where negative 4 pi third lives. Bless you. it would be rotating through 3 quadrants if it were positive, but because it's negative, this would be negative 3 pi thirds, negative 4 pi thirds. It's actually going to be in quadrant 2. It's coterminal with 2 pi thirds. The reference angle, though, is pi thirds. That's what's important for now. Now, in that quadrant where negative 4 pi thirds lives, is tangent positive or negative? It's negative. The PVR for our tangent on the unit circle, remember, is quadrants 1 and 4. Which of those 2 quadrants is tangent negative in? 4. So what we want to do is we want to get to quadrant 4, same reference angle, but we get there by going clockwise. How much? We go clockwise pi thirds, so the answer, good, is negative pi thirds. See how fun it is? It's a very systematic process. Figure out where the angle lives, find the reference angle, and then determine what the sign is, and then get to the other quadrant where it's the same sign, and then it's the same reference angle. All right, letter D, inverse tangent of 19 pi 15. 19 pi 15 is a what, an angle or a ratio? An angle. And it's not a odd pi thirds, or odd pi half, sorry, so it's a legal angle. It's not D and E, but 19 pi 15 is not in the PVR. So, we need to figure out where 19 pi 15 lives. Quadrant 3? Let's see. Pi, remember, is 15 pi 15. And if you want to know what you're counting by, take half of 15. What's half of 15? 7.5. So every time you go to another axis, you're counting by another 7.5. So down there at 3 pi halves, what is 15 plus 7.5? 22.5 pi 15. So now you can tell with certainty that as you go to 19 pi 15, you come around, but you don't quite get to the y-axis. This is 19 pi 15. Okay, so in any order, it doesn't really matter. Let's do it kind of in a different order. In this quadrant, quadrant 3, tangent is what? Positive or negative? It's actually positive, right? Negative x, negative y. So in the PVR, which is 1 and 4 for arc tangent, which of those 2 is tangent also positive in? 1. So I need to be in quadrant 1. That's the first thing. And now I know it's going to be the same reference angle. And in this case, the answer is the reference angle because it's a positive acute answer. So what's the reference angle between 15 pi 15ths and 19 pi 15ths? 4 pi 15ths. Good. And there's your answer. So this one is like the one in the warm-up. I like these types of questions because they do require old skills of figuring out where an angle terminates and finding the reference angle, but also then knowing what the PVR is, which really you're only memorizing 2 PVRs. Arc cosun is the only one that's different. Cosun, sun on the horizon. Cosun on the horizon. Okay, so that's if we do inverse trig function, or vice versa. But look at example 13 now. It says evaluate the following compositions without a calculator. Sine of arc cosine of negative square root of 2 halves. Do those have a shot at just undoing each other? No. Why? They're not inverses of each other. Sine and inverse sine are inverses. Cosine and arc cosine, but not sine and arc cosine. So how are we going to approach a problem like this? Yeah, we're going to use the unit circle. We're going to work from the inside out. Yeah, we just actually have to evaluate it. So let's go ahead and do that. Work from the inside out via the unit circle. Arc cosine of negative square root of 2 halves. What is the angle in the PVR for arc cosine where the cosine ratio is negative square root of 2 halves? 3 pi fourths. Good. It's got to be a quadrant 2 angle because cosine is negative in quadrant 2. And, of course, you recognize the square root of 2 halves as your pi fourths reference angle. So that's going to be 3 pi fourths. And now it's like an old unit circle quiz. Now that we're at 3 pi fourths, what's the sine ratio there? Positive square root of 2 over 2. Sine is positive in quadrant 2. Cosine is negative. Excellent. That's how you do it. It's a little 2-step process. Like one of those things you get at HCB, those 2-bite brownies. You ever seen those 2-bite brownies? Ooh, are they fooling? You could throw that whole thing in your mouth. Huh? That's right. Yeah, they're delicious. I'm just saying for the record, those 2-bite brownies, there's like 30 of them. I can eat the whole thing in 30 bites. All right, and then feel guilty afterwards, but sometimes it's worth it. Yeah. All right, letter B. Arc cosine of sine of 5 pi thirds. Whoa, hang on there. What are you doing? Are you evaluating sine of 5 pi thirds for me? Yeah. Okay, and what did you say? Okay, I didn't know if you were suggesting the number of bites it would take to eat a brownie. That wouldn't make sense, would it? Because it's an irrational number. That's an infinite number of bytes because it's a non-terminating decimal. And it's also negative, which means you're not eating a brownie, but rather, oh, yeah, don't do that. Gross. Okay, good. And now the new part, arc cosine of negative square root of 3 halves. Which quadrant? 2. And what's the reference angle? Pi 6. So now you're saying, okay, what's your pi 6 angle in quadrant 2? And it is, of course, 5 pi 6. What's cosine of 5 pi 6? Negative square root of 3 over 2. Hey, what's cosine of 7 pi 6? Also negative square root of 3 over 2. But why is the arc cosine of negative square root of 3 over 2 not 7 pi 6? Outside the PVR. Good. That's in quadrant 3. And we need to be in quadrant 2 or 1. All right, sweet. Inverse tangent of cosine of pi, inside out. What's cosine of pi? Is it 0 or negative 1? It's negative 1. It's the x value, right? Pi. Very important. We had a question on the previous exam where it was like tangent of A or cosine of B or whatever. And if you got the first thing wrong, then the whole thing derailed, right? Kind of the same idea. Cosine of pi is negative 1. Now, what is the inverse tangent of negative 1? Well, it's got to be in the PVR for arc tangent, so it's either going to be in quadrants 1 or 4. And which of those two is tangent negative? 4. So I'm looking for a negative acute angle where tangent is equal to negative 1. 7 pi fourths is a great answer choice for me to put on the test because it's coterminal with the one we want. 7 pi fourths is over there, but that's not how we get there, is it? We get there by going straight down, so it's negative pi fourths. Well, we from the unit circle, right? Tangent and cotangent are only equal to 1 or negative 1 at your pi fourths angles, because that's where it's both square root of 2 halves, right? So any pi fourths angle, your tangent and cotangent are 1 or negative 1, because your sine and cosine are either the exact same or opposite. So it had to be a pi fourths angle. All right, and then of course we get there by going clockwise by the acute amount pi fourths instead of all the way around to 7 pi fourths. Right? Putting it all together. Trig, trig, trig. Letter A, B, C, D comes next. I know my alphabet. Arc sine. Working from the inside out. Arc sine of negative square root of 3 halves. What's the PVR for arc sine? Is it the sun or the moon? It's the moon. So just like arctangent, if you start with a negative ratio, you're going to end up with a negative acute angle. So what is the angle in quadrant 4 then, where sine is negative square root of 3 halves? Negative pi thirds. Good. Negative pi thirds. Why not 5 pi thirds? Because you can't go all the way. Very good. All right. So now we're sitting at that terminal ray. What is the cotangent there? Well, you might want to write the ordered pair. The ordered pair at negative pi thirds is positive 1/2, negative square root of 3 halves, right? That's why we got arc sine as that, because it's the sine ratio. Cotangent is what in terms of x, y, and r? X over y. So if you get rid of the 2's, you're ending up with 1 over the negative square root of 3, which is negative 1 over the square root of 3. And of course, when you rationalize, it's negative square root of 3 over 3. It's fun. Inch by inch, it's a cinch, right? But you still have to know your unit circle. And now you have to know the PVRs as well. If you're kind of rusty on your unit circle stuff, Quizlet is open 24/7, 366 in a leap year. Right? So is Corpus World. All right, you do this one. Give you 30 seconds. This is more like the one from the test. What's sine of 2 pi? You can imagine all the wonderful answer choices I would have on a multiple choice test that are so tantalizingly delicious. Kind of like those 2-bite brownies. They also make 2-bite cinnamon rolls, which don't fool yourself. You can get those pretty easily in 1 bite as well. What is sine of 2 pi, Mr. Mims? 0. Okay? Now this one's kind of interesting because notice my inside function is sine, so 2 pi represents an angle. And when I take sine of 2 pi the angle, I get 0 the ratio, yeah? But I also get 0 the number. My next function on the outside is not inverse tangent, but what? It's tangent. So I have 2 angles back to back. So the output of 2 pi, sine of 2 pi gives me a ratio, but now it becomes an angle in this context. So what is the tangent of 0? 0 is 1, 0, right? That's the ordered pair at 0 radians. Tangent's y over x, so it's 0 over 1, which is 0. The answer is 0. Tangent of 0 is 0. It passes through the origin, right? It's your monotonic increasing function. I see it right here on Kieslin's notes, right at the top. Passes right through the origin. Okay? A, B, C, D, E, F comes next. Secant of, tangent of pi. Same thing. Trig function, trig function. This is not a composition of 2 inverses. Or even 2 inverse type of functions. What is tangent of pi? 0. Good. And what is secant now of 0? Those are all, you're giving me all kinds of great answer choices for a test. 0, 1, D and E, none of which one is correct? Negative 1? It's 1. Yep. Just got to make sure you're sure, right? Because the ordered pair at 0 is 1, 0, and secant is the reciprocal of which one? The cosine, and the reciprocal of 1 is 1. Yeah. Cool. Got a few more here. Here's the composition now of 2 inverse trig functions. Inverse cosine of inverse sine. So the 0 that we're starting with is what? An angle or a ratio? It's a ratio. So inch by inch, it's a cinch, hopefully. What is the inverse sine of 0? Sine of what angle is 0? Well, it has to be in the PVR, doesn't it? So where is sine equal to 0? Yeah, sine y. So it's 0. Arc sine of 0 is 0 because sine of 0 radians is 0. And now, what is the inverse cosine of 0, the ratio? In other words, cosine of what angle in the PVR for arc cosine is 0? No, cosine of 0 is 1. Pi halves. Good. Because what's cosine of pi halves? 0. Yeah. So here's a double composition of 2 inverse functions. The arcsine of 0 is 0 radians, the angle, but now because it follows an inverse cosine, it becomes 0, the ratio. And so the answer is pi halves the angle. Oh my gosh, I throw something like this and people get real excited. It's like, I didn't know this much fun was legal. I didn't know you could do this. Sure you can. You still take it inch by inch, it's still a cinch. And sometimes when things are a cinch, it's not real fun. But there's enough variety here to keep it fun. So what do you do with the 2 out front of the arc cosine? Nothing in the beginning is the answer. It's the second thing that you do. The first thing you do is, your dear Aunt Sally says, is to evaluate the arc cosine of a half. So then you'll take that, multiply by 2, and then take the sine. So what is arc cosine of 1/2? Pi who? Pi thirds? Anyone object? Anyone agree? Yeah, what is cosine of pi thirds? 1/2. So arc cosine of 1/2 is pi thirds. Excellent. And now I multiply. What's 2 times pi thirds? 2 pi thirds. Okay. And that is now a unit circle angle. So what is sine of 2 pi thirds? Which quadrant are we in? It's going to be square root of 3/2, but is it positive or negative? It's positive. Yeah, in quadrant 2, sine is positive. This is pretty much everything we've done so far from chapter 5.1. It's all coming together here. And then finally, you eat the elephant one big bite? No, you'll choke on the elephant. Why are you eating an elephant? That's kind of gross. They say it's easier, though, if you have to eat the elephant one bite at a time. So inch by inch is a cinch. I like that better. You have 3 compositions here. Just focus on one at a time. So let's work on the inside, and I'm just going to work straight down, and I'm just going to bring everything else down. Focus on one layer at a time. So what is sine of 3 pi halves? That's a piece of cake. -1? Campbell, you agree? -1? You do? Dallin, is that right? Sine of 3 pi halves is -1? You sure? I agree. Okay. Whew. Oh, man. Okay. So now I'm bringing down the secant, and I'm focusing on arctangent of -1, which I think we've already seen today. Tangent of what angle is -1 in the PVR? -pi4. Good. -pi4. And now we're evaluating secant of -pi4, which is really the same as secant of 7pi4 because they're coterminal. And remember, coterminal angles have the same trig ratios. So if you prefer, at this point, go to -pi4 and draw the ordered pair. It's positive square root of 2/2, negative square root of 2/2. And we want the secant ratio. Secant is the reciprocal of which one? X or Y? The X. So what's the reciprocal of positive square root of 2/2? Just the square root of 2. Good. We did that quite a bit when we were quizzing over the unit circle. Awesome. So that's like 3 problems in 1. That's real value as a teacher. Okay? 3 problems for the low price of 1. I like it. More bang for the buck. It's like shopping for math at Costco. Now, you might ask yourself, what am I going to do with 5 gallons of mayonnaise? Okay? I guess make a lot of tuna salad. But you never ask yourself, what am I going to do with 5 gallons of math? The answer is easy, right? I get to eat it. Lucky me. All right. National Fun Day. Yes. Yeah, gross, you can. Yes, Phipps. The only time the PVR matters, correct, is when you're taking an inverse. Inverse sine, inverse cosine, and inverse tangent. And you know what? There are 3 more inverse trig functions, aren't there? Inverse secant, inverse cotangent, and inverse cosecant. We're not even going to look at those. Sorry. You're just responsible for those 3. And remember, 2 of the 3 have the same PVR. Arctangent and arcsine, for the most part, minus the vertical asymptotes. Okay, we can also compose trig functions with inverse trig functions that are variable functions. Okay, the result is an algebraic expression that's equivalent for all values in the domain. This gives us what is to be known as an identity, and we're going to be studying trigonometric identities in the next chapter, okay, which leads into trig proofs. So what comes to mind when you hear the word identity? What's that? That's what comes to mind in today's day and age? Have you had your identity stolen? Twice. I'm sorry to hear that. I saw something for LifeLock online. Have you looked into LifeLock? Everyone just wants to be you. It's kind of a compliment. An identity, though, is who you are, right? You look in the mirror and you're like, hey, there I am. What a good-looking guy. Two people in California. They're fighting over you in California. Nice. Okay. Yeah, so an identity thief is someone who wants to be you, but is he really you? No. So if I say 2 equals 1, is that an identity? No, that's like the 2 trying to steal 1's identity, bless you, or the 1 trying to steal 2's identity. So that's identity theft. Or in mathematics, we call that not an identity. We say it's not true. But what if I say 1 equals 1? Is that an identity? That's an identity. When one looks in the mirror, who does he see? He sees 1. Okay? Now that's a very boring identity. It's a very boring identity. We're going to be looking at other identities, identities that have variables in it. I think the most popular one that you've seen so far is this. The absolute value of x is equal to the square root of x squared. What does the absolute value of x see when he looks in the mirror? Well, he still sees the absolute value of x, right? Because that's how mirrors work. So the analogy breaks down. These two things right here have a different phenotype. You know what a phenotype is? They have a different physical appearance, but they have the same genotype. They have the same genetic makeup, meaning that they are mathematical synonyms. You can replace one for the other without any loss of generality. You pick any x value in the world. If it works on both sides, you're going to get the same answer. Let's try it out. Pick a number. 734. What is the absolute value of 734? 734. What is 734 squared? 734 squared. What's the square root of 734 squared? 734. See? Let's try with a different number like -5. What is the absolute value of -5? +5. What is -5 squared? What is -5 squared? +25. What's the square root of +25? +5. So the order matters. In this case, if you square a number and then take the square root, it's the same as taking the absolute value of it. Notice this is not equal to this. If I take the square root first, what's the square root of -25? The square root of -25 is imaginary. It doesn't work. So they don't have the same domain. All right? Square root of -25 is an imaginary number, right? So in this case, I'm squaring it first, so negative numbers are allowed. So those two are identities. Order matters, all right? So that's a non-trivial identity. They have the same genotype. They're mathematical synonyms. We're going to do the same thing right here, right now. Write the following as an algebraic expression. This is pretty important when you get into calculus. You have something that is a trig function of an inverse trig function of x. I say that we can write it as an algebraic expression without any trig in it at all. Why would we want a different version that doesn't have trig? Well, maybe you don't like trig, right? Maybe algebra is more your forte. I say that there's an equivalent that doesn't have trig in it. And you'd be like, no way! And I'd be like, yes way. Prove it. Oh. Okay, I will. That x right there is my input. Does it represent an angle or a ratio? It's a ratio. How do we know it's a ratio? It follows arc. I'm going to make it look more ratio-esque. How do I do that? Put it over 1. Now, when I take the arctangent of that ratio, I'm going to get a what? I'm going to get an angle theta, and that angle theta is going to be in the PVR of arctangent. So it's either going to be quadrant 1 or 4. I don't know what x is, so I don't know if arctangent's going to live in quadrant 1 or 4. So here's what I'm going to do. I'm just going to draw a generic representation, just something to label. So you can always just draw it in quadrant 1. Every single one of the 3 inverse trig functions, remember, has a PVR that includes quadrant 1. They all have quadrant 1. Okay, so now, remember, when I have the ratio x over 1, I have 2 of 3 sides of this right triangle, yes? Tangent measures which 2 sides? Y and x. So notice it's x over 1, so it's a different x. From the unit circle, y over x is vertical over horizontal. So my vertical I can label as x, and my horizontal I can label as 1. Yeah. Sure. Someone stealing your identity again as we speak? Shut them down. Say, I am me. Right? X over 1, y over x. Got it? Now that I have the 2 sides, I can find the 3rd side by the what theorem? Pythagorean theorem. So here we go. I'm going to call this R for hypotenuse. Like the way Scooby-Doo would say it, right? So 1 squared plus x squared equals r squared. So what is r? I want to solve for r in terms of x. If I take the square root of both sides, I get 1 plus x squared. And now I'm going to get rid of that r up there. It was a temporary placeholder, and I'm going to put 1 plus x squared in its place. So now, if I knew what x was, would you agree that I would know then the value of all 3 sides? Yeah. Sure, yeah. I have them all written in terms of x. So if I have all 3 sides of this right triangle, don't I have all 6 trig functions at my disposal? Yep. So what do I want to end up with now? I want to end up with the cosine ratio of that angle theta. What is the definition of cosine in terms of x, y, and r? X over r. So that's the horizontal, which we're calling 1, over the hypotenuse, which is the square root of 1 plus x squared. And ta-done, there you go. These right here are mathematical equivalents. For all values of x in the domain of both of them, if you plug a number in on the left side, it's going to be the same number that you get when you plug it in on the right side. They are mathematical synonyms. You want to try it out? Let's try it out. Let's see if it works. Let's try a simple number like x equals 1. What do you get when you plug it into the left? You get cosine of arctangent of 1. We want to know, is that equal to 1 over the square root of 1 plus 1 squared? So what did I do? I chose an arbitrary value, and I plugged it into both sides. And I'm going to see if it works. The left side, what is arctangent of 1? Pi fourths. Excellent. Okay, so I'll work straight. You can draw a line down the equal sign. You want to evaluate these two independently. Now, what's cosine of pi fourths? Square root of 2 over 2. Excellent. Now, on the right side, let's evaluate. That's 1 over 1 squared is 1. 1 plus 1 is 2. So I have 1 over the square root of 2. If I rationalize it, what do I get? Square root of 2 over 2. It works. Yeah. So you don't even have to rationalize this. You can leave the radical in the denominator because it's a variable function. If you needed to rationalize when you plugged in, that's up to you. So there you go. We've kind of verified that these are, in fact, identities. One can replace the other. One of them has trig, one of them doesn't have trig. So two completely different looking things that are actually mathematical equivalent. Kind of nice. We call this a what? An identity. It's true for all values of x in the domain. All right, let's try this one. Sine of inverse cosine of 2x. Is 2x an angle or a ratio? It's a ratio. So you put it over 1, and then you draw a generic reference triangle, which you can always draw in quadrant 1. The inverse cosine of 2x is going to give you some angle theta. You don't want theta, you want the sine ratio of theta. So let's go ahead and label what we have. 2x over 1, that's going to be a horizontal 2x and a hypotenuse of 1. So really what I want to do now is find the other side, which temporarily you can call it y. So by the Pythagorean theorem, 2x quantity squared plus y squared equals 1 squared. And how do we solve for y? We'll take the square root of both sides, and we don't know if it's plus or minus depending on x, so we're just going to put the positive version here. And I get 1 minus 4x squared. You got to be careful when you square 2x. It's 2x times 2x. And so now that I know what y is in terms of x, I'm going to come back up here and get rid of the y. It was a temporary variable. And I get 1 minus 4x squared. And now that I have all three sides in terms of x, I have all 6 trig ratios. Which one do we want? The sine. So sine is y over r. So it's going to be the square root of 1 minus 4x squared all over 1, which we don't even need to write. So there you go. We have now established another identity. It's important to notice under the radical. Notice under this radical, I had something plus something. Whenever you have something under radical and something plus something, the square root of those two numbers are your short sides, right? Because that's how you find the hypotenuse. 1 squared plus the other squared. Whereas if you look under the radical and you have something minus something, then that's going to be your hypotenuse squared minus one of the short side squareds. Okay, that's kind of important for the next example when we go backwards. Letter C. Oh boy, cotangent squared of arc cosine of x squared. Here's what you want to do first. This squared is kind of important. What are we actually squaring there? The t, the COT, or the what? We're squaring the cotangent ratio. Yeah. So if you ever see something like that, that's condensed notation. You want to write it, first of all, as the whole thing squared. We're squaring the cotangent ratio. It's just easier to transport when it's written like that. Cotangent squared is the same as cotangent quantity squared. So if you rewrite it like that, now that's kind of the last thing we take care of. On the inside, I have arc cosine of x squared. Again, if you want to put it over 1, not a bad place to start. I'm now going to draw a generic angle, theta, in quadrant 1, because the arc cosine of x squared gives me some angle theta. Don't really care what theta is, because I'm interested in the cotangent ratio. All right, so once again, we'll label it cosine from the unit circle is x over r. So I'm going to label my horizontal as x squared, and I'm going to label the hypotenuse as 1. Now, all I got to do is find the y again. I'm not going to call it y temporarily because you don't have to. You should be able to do it in your head. This short side is going to be the square root of hypotenuse squared minus the short side squared. We just did the work up above. If you need to call it y and go off to the side, feel free. But it's going to be the square root of hypotenuse squared, which is 1 squared, minus x squared squared is x to the 4th. You should be able to do that in your head. But again, if not, do it off to the side. Call it y temporarily, use the Pythagorean theorem, and solve. All right, so now that we have all three sides, we essentially have all 6 trig ratios. So now I'm going to pull off which ratio? Cotangent. Cotangent is x over y, so that's going to be my horizontal over the vertical that I just found. Now I'm not done because what's the last thing I need to do? The whole thing is squared. And now I will square both the numerator and the denominator. So x squared squared is x to the 4th. And what happens to the denominator when I square the radical? I just get the radicand, and there's your answer. Okay? I think that's a good place to stop. We actually didn't finish. I don't want to rush example 15 because it's going backwards. We're going to be decomposing algebraic expressions into trigonometric ratios, and it's always a little more fun to go backwards. Yes? So the homework is not due tomorrow. We probably will not quiz tomorrow either. We'll probably quiz on Wednesday, okay? So we're off by a day already. Nothing like getting behind on a Monday. Yes, ma'am.